We're studying rational functions this unit, and a typical rational function is written as a quotient. A rational function is to polynomial functions as a rational number is to integers. You build a rational number from integers by doing a division problem, an integer on top and a non-zero integer on the bottom. A rational function is a polynomial on top and a polynomial on the bottom. I'll use this language, P of x and Q of x, because that's what was in the lab. When I was doing it in lecture the other day, I called it n of x and d of x for numerator and denominator, but the point is that it's still something that comes out as a series of powers of x with coefficients that get added up. And that's how you build a polynomial. You do it top and you do it bottom. And coming up with what the graph might look like, again, language from the lab is to look at features of a graph. If you ask about features of a car, you might say how big the engine is, or whether it's got bucket seats or a bench seat, or whether it has a CD changer in it, or whether it has a responsive cruise control. Lots of things that you could have as things that could be in a car or could not be. Features of a graph are things about the graph that might be there. If it's something that the graph has as a property, you can use that to get more information about what the graph looks like. And the kind of features of a graph might be x-intercepts or y-intercepts or vertical asymptotes or horizontal asymptotes. What other things might you have? You might have maximum values or minimum values. Places where the function gets about as big as it can or about as small as it can over its whole domain or over a restricted domain. I'm thinking like the vertex of a quadratic function gives a maximum value if the quadratic is aimed up, or if a quadratic is aimed up, it gives I guess that's a minimum value. If the quadratic graph, the parabola, is aimed down, then the place where the vertex happens is a maximum value. That might be something that's worth noting. And what makes it a feature is that it's just something that is useful to use to describe what the graph looks like. And the game in understanding rational functions is to interpret what features of the graph are in terms of properties of the polynomial. And here's the kind of thing that you might notice, that the x-intercepts of f of x, that's where f of x equals 0, p of x over q of x, that quotient of polynomials, is equal to 0. And the point that's been made a few times is that if you've got a rational expression, p of x over q of x, and that's supposed to be 0, that happens where p of x equals 0. So knowing about polynomials tells you about where the x-intercepts of that rational function are. And to find them, you've got typically a polynomial equation to solve. Y-intercepts, there's only one y-intercept, at most one, for a rational function, and you figure it out by evaluating the rational function at 0. We talked about vertical asymptotes. That happens where the function denominator is 0. So you look for q of x, the denominator of the rational function. The bottom equals 0, and you exclude 0 values. So maybe the best thing to do is to look at some examples again and think about identifying features. And that's very much what the problems were on MyLabs Plus. So here's a homework from the graph of a rational function. This is a section that comes after the section about properties. The properties of a rational function kind of fit as those features that we were talking about. And now to figure out how all that information interacts to come up with what the graph looks like, you can do it via this sort of taking in inventory. So one thing, so the analyze the graph of a function. What's the domain? You want to exclude zeros, 0 values of the denominator. And I'll do that by saying the denominator is x times x plus 14. It's already given in factored form. If I set that equal to 0 to see where I get in trouble, one factor is x, that could be 0, and the other factor is x plus 14. That could be 0, and that would make x equal minus 14. So that the domain would be x not equal to 0 and not equal to minus 14. Notice that x plus 4 is 0 when x is equal to minus 4. But x equals minus 4 makes the numerator of that fraction 0, and a fraction with a 0 on top is just fine. It has a value of 0 as its as the function value. That certainly makes sense. It's something that is in the domain. So it's only those two values that need to be excluded. So we can get that part done. What's the equation of the vertical asymptotes? And I want to write this down as vertical asymptotes happen where I have a factor that would give me dividing by 0 and dividing by 0 where I have a non-zero numerator. That'll make it so that I've got a fraction whose value grows without bound, the spike in the graph that the vertical asymptote looks like. So it looks like I have that at 0 and at minus 14. So I'd say x equals 0. Notice that is the equation for a vertical line. X equals 0 means x equals 0 no matter what y is. So that counts as in the coordinate plane as the equation of a vertical line. And another vertical line would be x equals minus 14. So those two together are the values for x equals 0, x equals minus 14 as vertical asymptotes. Let me clear my ink now. Well, let me capture it while I've got it here. And now I'll clear my ink. What's the equation of the horizontal or oblique asymptote? Well, here's what I'm going to think about. There is a rule of thumb that you can use. It is that when you've got a rational function, the top polynomial has a certain degree, the bottom polynomial has a certain degree, and if you look at the comparative sizes of those two degrees, it tells you about what the asymptotes are. That's measuring the end behavior of the function. So that end behavior, the horizontal asymptote, exists in this case because the degree of the bottom is 1 bigger than the degree of the top. It grows faster so that values are coming out from the bottom are bigger for large values of x than values on the top. That makes the rational function tend towards 0 in the long run, and that's the horizontal asymptote. the value would be y equals 0. I think about it when I'm doing it for myself in terms of sizes of numbers, big numbers, small numbers. Maybe your approach is a more specific one. Maybe you would prefer to do a calculation and look at particular numbers that come out to see why it works as it does. So if you call up a calculator, just to watch it happen, and you calculated x plus 4 over x times x plus 14. Say you do that for x equals 1, then it would be 1 plus 4 is 5 divided by I was plugging in 1, so 1 times 1 plus 14, 1 times 15 divided by 15. 5 divided by 15 is 0.33. Now let's try it for a bigger value of x. Let's try it for 10, just to see what happens. So I've got 0.33 in that case. If I tried doing that for 10, I would have 14 divided by, and the denominator would be, I'm plugging in 10, so 10 times 10 plus 14 is 24. So just doing a calculation, 14 divided by 10 plus 24 is what I get when I plug in x equals 10. And the value overall for that fraction is, look, 0.058. So I've got that 0 out front. It makes the fraction smaller. One more example. Suppose I go up and use an even larger value of x. Suppose I plug in x equals 100. Then it would look like 104 divided by, and the denominator would be x was 100 for that particular function value, and x plus 14 is 114. And this time, what comes out is for that big denominator, look at all those zeros out front. The bigger I make x, the closer that ratio that defines the rational function gets to 0. So that horizontal asymptote should be x equals 0, and or y equals 0. So let's see if that's right. And yeah, good. What's the equation of the, so I've got that, which graph is the correct graph? So it's nice to have a set. What we've got to come up with is an x-intercept at -4. So let's look at these and see if we can find. So I want to look at those graphs and identify these as the features. I want an x-intercept at -4, 0. I want vertical asymptotes at 0, x equals 0, x equals -14, and I want a horizontal asymptote at 0. So let's see which of those, see if any of these have the effect of doing that. Looks to me like another thing that I might notice is that for positive x, so big positive x makes r of x positive. Plugging in a number for x and do the arithmetic, a positive number for x divided by, for the numerator, divided by a positive number for the denominator makes the answer positive. So that makes me think the long-term answer ought to be this one, or this one. Those are where the positive values would be. And otherwise, what else can I say? It has to cross the x-axis at x equals 0, or x equals minus 4. So this one would do that. I'm watching the value go from negative to positive to negative to positive, as that r of x does. So that of all those 4, only this one catches all those features and has that pattern of signs. So I think that would be the right answer. These are good to mess with. A lot of times you'll find that at the end of the problem, when you've gotten this information, you can look at a graphing utility, pull out your calculator, or use the graphing utility that we provide in the labs, and see if all the information that you've uncovered about the function is consistent with the picture that you come up with. When we come back next class, we'll talk more about polynomial functions. It turns out that for low-degree polynomials, figuring out what zeros of the polynomial function are, to find out the x-intercepts or the vertical asymptotes, is not too hard. Factoring works, but we'll go back and pull in synthetic division to figure out that information for more complicated polynomial functions. That's what's coming next. Okay, well, we'll be back in business tomorrow.